Greetings to all and welcome to this lecture. We are in module 5, lecture number 4, Complete All Region Model part 1. In this lecture, we will see how we can derive the all region model in the sense which is applicable for weak, moderate and strong inversion. We will also find some fruitful relation between charge, voltage and current. These are the learning outcomes of this lecture, which tells you that how we can find out the current in the MOS transistor, which is nothing but a component of drift and diffusion. We will see how we can maintain a balance between drift and diffusion by formulating the current of MOS transistor in terms of surface potential and inversion charge. Let us do a quick recap. In previous lecture, we analyzed the 4-terminal MOS transistor as an extension of 3-terminal MOS structure. We said that we can use another 4-terminal to connect this inversion layer with external supply. We have identified the band diagram of this MOS transistor in various conditions. Here we said that when the gate voltage is small enough, then there will be a potential barrier exist between this N plus region and P type body. That is what is represented by Q into 5Bi. According to that, the surface potential is almost 0. So here A dash line shows the surface potential corresponding to the potential energy A. We said that keeping VSB is equals to VDB, if we increase VGB, then this junction becomes forward bias. If you apply the voltage at this side, you can see that this P side and N side become forward bias because you are keeping this as constant and you are increasing this voltage. Accordingly, the surface potential at this side will be increases, and the increase in surface potential reduces the barrier. If the barrier is reduced here, then the electron which is available here, earlier it was facing a potential barrier height and cannot go from source to channel. But now what happened when you increase VGB, because of this barrier lowering, the electron can easily go into the channel from source. This barrier is available, but it will not rise or it will not give the current because you maintained VSB is equals to VDB. It means there is no horizontal field exist. To do that, we are applying VDB greater than VSB. If we apply such a way, then the potential energy at the drain side will get reduced, and hence there will be a bending in the bands. That is what we have seen in previous lecture. Because of this bending, there is field exist, and because of this field, the carrier which is coming from the source get attracted by this field and give rise to a current. Corresponding to this band bending or band lowering, we do have a surface potential rise from source to drain. We also considered that for simplification we are neglecting the transition region, meaning we are just assuming that the depletion region is expanded at the P side and there is no expansion of the depletion region in N side. Further, we said that the channel length is wide enough between 0 to L such that these transition at very close to these regions can be ignored. For example, this transition is happening between 0 to 0 dash and this is happening between L dash to L. We are assuming that L is so high that such that we can simply ignore this, and hence L is nothing but overlap to L dash, or you can say L dash is overlap to L, and similarly 0 dash is overlap to 0. That is what we have plotted the surface potential between 0 to L dash only, but it shows the overall surface potential between 0 to L. Further, we mentioned that we are assuming gate current is 0 and substrate current is 0. Let us derive a complete all region model. Here complete stands for no simplifications have been considered, and all region stands for that this derived equation will be applicable to capture all region of operation, that is weak inversion, moderate inversion and strong inversion. To move forward, we will assume that this is a inversion layer representation. These all region model will be derived for one approximation, that is charge sheet approximation, meaning the inversion region thickness is infinitesimal small. We have discussed this approximation when we are discussing the two terminal MOS transistor. So, this is oxide and this is gate, this is source, this is drain, n plus n plus. The moment you apply gate, ultimately the channel first get depleted and then the inversion region forms. So, our assumption is the thickness of this inversion region is infinitesimal small. So, this is a representation of the inversion region. We assume that the thickness of the inversion region is very small and we are following towards the x direction how my surface potential and the charge varies. So, this is the point where the surface potential is psi s x. This is the point after delta x where the surface potential is changed from x to x plus delta x. So, this is nothing but the change in surface potential along this direction and this is due to result of applied VDS. At any point in x, the current is nothing but given by the drift component plus diffusion component. So, we can simply write Ix is nothing but I drift x plus I diffusion x, right. We can find out the component of I drift and I diffusion from our previous analysis. If you remember, in our module number 1, we have extensively analyzed the drift and diffusion for a piece of semiconductor having these dimensions. B was the width, A was the length and C was the height. We said that if we apply the voltage in this bar, then the charge will move from this side to this side and the transit time was nothing but A divided by Vd, where Vd is a drift velocity. Similarly, the total charge comprises in this region can be given by N into Q into ABC, where ABC is the volume and N is the concentration of electron, Q is the electron charge. If we really want to show this charge in terms of charge per unit area, then we can simply rewrite as N into Q into C into AB divided by AB, where AB is the area which we see from the top. So, this is B, this is A. So, we can represent the charge per unit area as N into Q into C. Now, the drift current can be given by I is equals to total charge per transit time, which is nothing but N into Q into C into A by B divided by A into Vd. This get cancelled. This can be written as Q dash into B into Vd. Vd is a drift velocity which is nothing but bulk mobility into electric field. Here we are assuming a different mobility than the bulk mobility, which is mu, and electric field is nothing but delta psi s by delta x, right. This is the change in the surface potential in x direction with respect to x. This is nothing but the electric field which is exist in the horizontal direction, right. So, this will give me the drift component of the current as a function of x. That is what we are getting here. Here we should take care that the charge is nothing but inversion charge which is negative, and hence we are getting this equation as mu into W, because in this analysis this W is our width. In earlier analysis B was the width. So we just replace the parameter B by W. Q dash is replaced by Qi dash because we are talking about the inversion layer, and the electric field can be written as d psi by dx. The reason for replace this mobility mu by mu and not taking mu b is as follows. If you have n plus and n plus and this is bulk p type, the electrons move in this bulk with a velocity mu b, but the moment electron comes near the surface, ultimately they will flow or they will move under the vicinity of vertical field, and hence the flow will be not normal as the flow or the mobility will be not normal as the mobility present in the bulk. The electron will flow with some vicinity of vertical field as well as the surface roughness between Si and SiO2. That is what, to capture all these effects, we replaced mu b by mu. In a similar way, the diffusion has been defined with the same analogy as the diffusion current is nothing but Q times Bc into dN by dx into dN, where dN here is diffusion constant. By using Einstein equation, we can simply write mu into phi t. B in our case is W. Q into C into N is nothing but inversion charge. So we can simply write the diffusion current as B can be replaced by W, this D can be replaced as mu into phi t, and this can be written as dqi dash by dx. Remember, we do have a negative gradient of electron which give rise to a diffusion current, and hence because of this negative, the negative of inversion charge get cancelled and we are getting this equation. And at any point of x, we will get the total current as I of x is nothing but mu into W into minus of Qi dash d psi s plus mu into W into phi t into dqi dash by dx. We are assuming that under DC steady state, the total current in the channel must be same for all x, right, and equal to nothing but the drain to source current. So this Ix is can be written as Ids. To further move and find out the relation between surface potential charge and current, we will integrate this between the limits as we have defined earlier, that this is 0 and this is L. So we will integrate our equation between 0 to L with integrate along the x, which give rise to a total current. So total current Ids is independent of x as we mentioned. So Ids can be written as Ids into L, and at the right hand side we will get W into integration of psi s0 to psi sl mu into minus Qi dash into d psi s, where psi sl is the surface potential exactly at this point, meaning the surface potential near to the drain side. Similarly, the psi s0 is the surface potential at source side. Keep in mind that we are ignoring the edge effects, and hence 0 dash is coincide with 0, such that this point is nothing but exactly at n plus p junction. Similarly, we can define Qi0 dash and Qil dash, which is the inversion charge at source channel junction and the inversion charge at channel drain junction. So following this notations, we can rewrite our equation as Ids is equals to W divided by L. So we are getting L from here at the left hand side, we are just putting in denominator into psi s0 to psi sl mu into minus Qi dash d psi s plus phi t integration Qi dash 0 to Qil mu into dqi dash. This is equation of current which comprises both component of drift and diffusion. Now we can define these individual components for the further analysis as IDS1 and IDS2. So we can simply write IDS is nothing but IDS1 plus IDS2. Here IDS1 is can be given by this and IDS2 is can be given by this. Strictly speaking, here IDS1 and IDS2 is not showing the drift and diffusion current component at particular x. It is the mean values over the x. So let's go further and derive the separate components of IDS1 and IDS2 by finding a relation between Qi dash and surface potential. So from our previous analysis, we know the potential balance equation is can be written as VGB is equals to phi ms plus psi s plus psi ox, where psi ox is can be written as Qg dash divided by C ox dash, and this Qg dash is can be replaced by a charge balance equation as minus Q naught dash by C ox dash minus Qc dash by C ox dash, where this term and this term forms a flat band voltage plus surface potential minus this Qc dash is the total channel charge, which can be rewrite as Qi dash plus Qb dash by C ox dash. By simplifying this equation, we will ultimately get this. And now what we will do, we will put this equation back to our formulas of IDS1 and IDS2. If you keep it here, ultimately IDS1 can be rewritten as W by L. Now we are assuming that mu is, or the mobility is also constant, though it is not the practical case, but for simplification we are assuming the mobility is constant and we are taking it out from the integral. And then because of this negative sign and negative sign, you will get Cox dash integration between psi s0 to psi sl VGB minus V flat band voltage minus psi s. This negative and this negative again it becomes positive into W by L mu integration of psi s0 to psi sl q b dash d psi s. If you simplify this and do the integration between the limit of psi s0 and psi sl, you will get VGB minus V flat band voltage into psi sl minus psi s0 minus this, the integration of this is nothing but psi s square by 2. So ultimately you will get 1 over 2 and put the limit psi sl square minus psi s0 square plus W by L mu times psi s0 to psi sl, you need to integrate the bulk charge. So this is a closed form equation for IDS1. In a similar way, you can put this Qi dash here in IDS2, where IDS2 was nothing but W by L mu into phi t integration Qi 0 to Qil dQi dash. If you do this integration, ultimately you will get what? Qi dash L minus Qi dash 0. That is what mentioned here. And now just replacing this Qi by Qil and Qi0, you will get this expression. So when you put Qil dash, ultimately you are writing W by L mu into phi t minus Cox VGB minus V flat band voltage minus psi sl minus Qb dash at psi sl. That is what this term is coming up. So ultimately the closed form equation for IDS2 can be written as W by L mu into Cox dash phi t into psi sl minus psi s0 minus W by L mu into phi t Qb dash psi s is a function of psi sl minus Qb dash as a function of psi s0. Let us further simplify by knowing that the bulk charge is can be written as minus gamma Cox dash into root psi s. Again you need to replace this psi s by psi s0 and psi sl if we are talking in terms of source and drain, and you can replace this Qb dash in terms of Qi dash, and finally when you put that, so let me solve for IDS1, which is nothing but W by L mu into C aux dash VGB minus V flat band voltage into psi s L minus psi s 0 minus half of psi s L square minus psi s 0 square. Now minus W by L into mu into C aux dash integration of Q B dash, meaning minus of gamma C aux dash into root psi s. So here no C aux dash will come. Now this minus and minus become plus. W by L mu into C aux dash is common, gamma is common, and now when you integrate this, ultimately you will get psi to the power 3 by 2 into 2 by 3, and you will get psi s 0 to psi s L. Again this was plus. So if you take W by L mu into C aux common, ultimately this is common, you are getting the same equation which is derived earlier here by putting QB dash in terms of this. So you will get VGB minus V flat band voltage into psi s L minus psi s 0 minus half of psi s L square minus psi s 0 minus 2 by 3 gamma factor is coming here into 3 by 2 power of psi s L minus psi s 0. Similarly, you can put QB dash here in previous equation and you can calculate IDS2, where you are taking W by L mu into C aux dash common and you are rewriting phi t into psi s L minus psi s 0 plus phi t into, so it is nothing but phi t into gamma root psi s. So when you put psi s L, ultimately it will become psi s L to the power 1 by 2 minus psi s 0 to the power 1 by 2. If you want to write a closed form equation of IDS, you can take W by L mu into C aux dash common and you just rewrite this plus this part, which will give you the closed form equation of IDS, which comprises all region of closed form equation of IDS. Let me summarize that in this lecture we have derived a all region model of the drain current comprising the drift component and the diffusion component, which says that we are considering the charge sheet approximation and it is applicable for all region of operation, that is weak inversion, strong inversion and moderate inversion. In subsequent lectures we will simplify our analysis. In subsequent lectures we will simplify our analysis to find a easy method to analyze these equations. So we will stop here for today. Until then, take care.